Today we're going to be talking about taking the derivative of a function which is the same as the original function. So in other words, when you take the derivative of this function, you get the same thing out. So if I were to say, what's the derivative of f of x? Well, in this case, it's f of x, right? So we'll talk about that. You may feel like we've kind of already done that, and specifically maybe a problem that might look something like this. If I say y equals sine of x, and I say take the derivative, well, the derivative of sine of x is cosine of x. That's not the same thing. The second derivative is going to be negative sine of x. The third derivative will be negative cosine of x. And then the fourth derivative will be sine of x again. So there is some sort of reciprocation. You can also say, well, cosine of x is actually just a horizontal shift of sine. So we can say that cosine of x is actually equal to sine of, right, x. Well, let's see, what does this look like? Sine looks like this, and cosine starts here. So what we need to do is take the cosine function and shift it to the right, so we're going to put minus there, pi over 2. So in a way, they're kind of related to each other. In a way, the derivative is the same as the original, but it's not. It's not the same. We wouldn't get the same result out. So what is this function? Well, if you think through all the different functions that we've talked about so far, we've talked about polynomials. We've talked about linear, obviously. We've talked about trig functions. We've talked about inverse functions and inverse trig functions. We've talked about radical functions and rational exponents. We've talked about rational functions where you have a fraction. So what is the one thing or two things that we haven't talked about so far? Well, the answer to that is we haven't talked about exponential functions and we haven't talked about logarithmic functions. So with that said, the derivative that is itself is an exponential function, but a very specific one, okay? There is a function that produces a derivative equal to itself. In other words, f of x equals f prime of x equals f double prime of x equals however many derivatives you want to take, it will always be equal to each other. What is that? Well, with your calculator, if you were to graph y equals e to the x and its derivative, you would actually see that they are the same thing. So let's go ahead and take a look at just an exponential function in general. We know what exponential looks like. We know that most exponential functions, if there's no shift to them, will have a y-intercept of 1, and they will have a horizontal asymptote of y equals 0, and they grow exponentially. Well, depending on, so this might be e to the x, depending on the base, so maybe if it was 3 to the x or something like that, you would end up with something that might end up steeper, right? It will grow faster because e to the x is not as big as 3. And then if it was less than e, what's e? E is 2 point something. So if it was y equals 2 to the x, then you would get something that grows a little flatter, but it still grow exponential, okay? But if you were to graph the derivatives of an exponential function, think about it. What can we say about this graph? Well, this graph is always increasing. Exponential function is always increasing. What does that tell you? That means the derivative of that exponential function will always be positive, right? If a function is increasing, then its derivative is positive. Well, what do we see? We see that all exponential functions are positive. So that kind of matches. And then if I were to look at the slopes along this graph at different points, well, what do we see is happening to the slope? The slope is increasing. It's getting steeper and steeper and steeper. What we call that is concavity. We see that this graph is concave up, and we'll get more into this when we talk about in Unit 4. But when the function is concave up, that means that the derivative is increasing. So what can we say? We can say that this function is concave up and it is increasing. That would imply that its derivative will be positive and increasing, positive and increasing. So they kind of match, they kind of go together. It makes sense that the derivative of an exponential function is going to be directly related to itself, to the original thing. Specifically, e to the x, right? So this is a big and important derivative because we use it, we build upon it when we talk about all types of exponential functions and all type of logarithmic functions. The idea of e to the x. The derivative of e to the x is e to the x. And this, ladies and gentlemen, is why e is defined as an important point, okay? Y equals 3 to the x, the derivative of that is not 3 to the x. The derivative of 2 to the x is not 2 to the x. But we recognize that there is an exponential function that will be the derivative of itself, essentially. And so we define that specific base to be the number e. And as we explore, we narrow down that value to be the defined value of e. So the derivative of e to the x is e to the x. So like before, you talked about, these irrational numbers. The two most important irrational numbers are pi and e. Pi is related to circles. The reason e is so important is because of the idea of the derivative, or at least one of the reasons it's so important, okay? So another way of saying that is if y equals e to the x, then the derivative is e to the x. Okay, so with that said, all the rules still apply. You still have the product rule, the quotient rule, the chain rule, implicit differentiation, all those things still apply. So we're just going to do some practice with taking derivatives of an exponential function of e to the x. Okay, so with that said, we've got number one, it says let f of x equals 7e to the x. F of x equals 7e to the x. Well, what rules can I apply here to figure out the derivative? Well, I have a constant multiple, so f prime of x is going to be equal to 7 times, if you want to write it out, the derivative of e to the x, right? We take the constant multiple out. Then we take the derivative. Well, what's the derivative of e to the x? It is e to the x. And then we put that 7 right out in front. So that is our answer there. The derivative of 7e to the x is 7e to the x. All right. Number two, it is looking for the derivative in respect to x of cosecant of 2x plus e to the x. Okay, and so we're looking for the derivative of this. I have a sum here, so that means I can take the derivative of each piece, and I'll go ahead and do that because it's just good practice to write it out. So I'm going to take the derivative of cosecant of 2x. And then I'm going to add to it the derivative of e to the x, just so I can see it a little bit here. Well, notice here I've got a chain rule because I have a function inside of a function. I have a composition. So what's the derivative of cosecant? Well, that is negative cosecant of the argument times cotangent of the argument, and then times the derivative of the inside, which is 2. And then we add to that the derivative of e to the x, which is e to the x. And we could simplify this a little bit by moving that 2 out front, but not much more. All right, so that is my derivative there, okay? For number 3, it says y equals e to the 2x. And I like this one because it helps us recognize where we see compositions even more. You see, when I have parentheses and I have something inside there like cosine of x and I raise it to the 4th power, it's easy to see that this is a composition. It's something raised to the 4th power. But students sometimes have a hard time recognizing that this actually is a composition of functions. This would be rewritten as u to the 4th if you wanted the inside to be labeled as u. Well, here, what is the input? So in this case, the input is u turning into cosine of x. So the input is x, and the result of that, we take the cosine of, and then after that, we raise it to the 4th power. So if you think of your order of operations, what would we be doing here first? Well, we'd be multiplying the 2 and the x together and then raising it to the e, which means the composition has the inner function as the exponent here, okay? So when I go ahead and use the chain rule to do this, maybe we'll do it the long way here. We'll say let u equal 2x. That would imply that y equals e to the u. And then we want to take the derivative of u in respect to x and the derivative of y in respect to u. Well, the derivative of u in respect to x is just 2, and the derivative of e to the u, or derivative of y in respect to u, is e to the u. So then we multiply those together. We end up with 2e to the u, or when I replace it, I get 2e to the 2x. And so that is my derivative there. If you want to see it a little bit simpler, you could just identify that 2x is the inner function. So what's the derivative of the outer thing? The derivative of e to the anything is e to the anything, e to the whatever that is, times the derivative of that anything. So times 2 times the derivative of 2x. So you can see it's the same result. Okay? So that's number 3 there. And then number 4, it says if a is a constant, and we have, I better erase this because I might need a little bit more space here. Number 4, a is a constant, and we have y equals a times e to the x squared. And we're looking for y prime. Again, recognizing that we have a composition of functions. What is the innermost function? Well, the innermost function is x squared, because that's the first thing I would do to simplify this expression. So what's the derivative of the outer thing? What's the derivative of a times e to the something? Well, that would be a times e to the something, because the derivative of e to the something is itself. And then times the derivative of the inner thing, so that would be times 2x. And so we can simplify that to say 2ax times e to the x squared. And I know for students it's like, okay, we have variables, and we've been learning for years that a variable is represented by a letter, and it is. But a variable is something that can change when we're talking about functions, right? We're looking at different parts of a graph, when x equals 1, when x equals 2, when x equals 3. So a variable changes, and then the output value changes. A, even though it's something that we don't know, it's not something that's changing. It's a constant. It's remaining the same. And so we have to treat it as a number, like 5, right? If I said, what's the derivative of 5e to the x squared? Well, it would be 5e to the x squared times 2x. Okay? If I were to do this the little bit longer way, I would say let u equal x squared. That would imply that y equals a times e to the u. Taking the derivative of each of these, we get 2x here, and then the derivative of y in respect to u, that's a constant, so take that out, and then multiply it by the derivative of e to the u, which is e to the u, and we end up with 2x times a e to the u, and u was x squared. And so you can see it's the same thing there. All right, so those are some good practice problems on taking derivatives when you're talking about the exponential function y equals e to the x. All right, now with that said, this next slide is going to be an interesting one. And this slide is talking about the spread of Ebola. Okay, now 7 years ago when I created this lesson and I was creating the calculus curriculum, Ebola was the big thing. It was the big infectious disease that was going to ruin the world. Everybody was worried about it. And so I just created a model. I made up the model. It has nothing to do with real numbers. But there was something interesting to note about all infectious diseases, right? And we'll talk about that in a second. The reason I'm really emphasizing this is because now in 2020, the big thing that has affected the entire world is the coronavirus. All right, so it's worthy of talking about and discussing a little bit so we understand a little bit of how these things work. First of all, a model that represents the number of infected people usually follows the same exact graph. When I say model, I'm saying I'm taking the data that I collect on how many people were infected with this disease, right? And I'm taking that data and I'm creating an equation that represents that data. That's what a model is. Okay, so all models generally follow the same routine, the same basic function, right? So we have exponential functions, we have polynomial functions, we have trig functions. Well, this is the model, or this is the general function that represents, not this particular one, but there is a general function that represents all infectious diseases or all types of growth, okay? And if you were to graph this, it says the spread of Ebola is modeled by the equation P of t, and that's equal to 100 over 1 plus e to the 3 minus t. If you were to graph that on your calculator, again, this is not the exact model for Ebola. I just kind of made that up. I just want to clarify that. But if you were to graph the spread of Ebola, you would have an initial person that had it, and then it would grow almost exponentially, and then it would flatten out, okay? That's generally the shape of all infectious disease, how it spreads. You get more and more and more people being infected, and this is not accounting for recovery at all, but you get more and more people infected, and as you get more people infected, it starts growing at a faster rate, right? But then there's a point where the rate starts to decrease for multiple reasons. Number one would be that a mass number of people have already gotten the disease, and therefore they're not going to re-get it necessarily. Another reason is some people might be immune to the particular disease, whatever it might be. Their genetics just makes them immune. But we can see that we start tailing off, and it will always kind of grow, but you're going to end up with some sort of horizontal asymptote at the top there. And so that's referred to as maximum capacity. And again, there's multiple reasons for a maximum capacity. One reason could be that everybody on the planet was infected, and therefore you can't have more than everybody on the planet, and that's your maximum capacity. That's a possibility. But in reality, some people are immune, you're not going to get people getting it multiple times or anything like that necessarily, okay? So that's the idea of the spread of infectious diseases. That's the growth, okay? And before we get into this problem, I'm just going to give you a little caveat in dealing with the coronavirus, because you would say, well, then why can't we just create a model for the coronavirus and predict when the spread's going to decline or the amount of people is going to kind of maximize? The problem, one major problem, is the way that we are accounting for our data, right? Not all infectious diseases are calculated. The data is not calculated the same way. Coronavirus has been looked at differently. Like many people are being tested that wouldn't normally be tested for some other types of infectious diseases. Not saying that's positive or negative, but the point is the data that we are looking at with the coronavirus does not mirror the data of a normal infectious disease. That's not because it's a different type of infectious disease that no one's ever seen before. It's because the way that we're reporting the data is different. And so to create a model to predict becomes very difficult. Now, 10 years from now, when we look back on it and we can see that data as a whole, it's probably going to follow that exact or a general curve that I just showed you a second ago. But for now, since we're in the middle of it, it's kind of hard to create that model, especially because we're collecting that data and we're reporting that data differently than we ever have with any other infectious disease for multiple reasons. Not worth getting into because we're talking about math here. Now, so P of t represents the number of people that were infected t months after the disease was first noticed. Part A says how many people were initially infected. So P of t is equal to 100 over 1 plus e to the 3 minus t, okay? And we want to know how many people were initially infected. Well, that means at the beginning, how many people did we have that had this disease? Well, that would imply that when t equals 0, so all we're looking for is p of 0. That's my initial population of people that were infected. So it'd be 100 over 1 plus e to the 3 minus 0. And then that would simplify to 100 over 1 plus e to the third. And this is when you're going to get your calculator out and evaluate that. So 100 divided by parentheses 1 plus e to the third power. And we end up with 4.723. Now again, this is a model, so it's a representation of reality. We can't have 4.7 people infected, so we would say, rounding, there were 5 people that were initially infected. Now other maybe it wasn't 5 people that were infected. There would be 1 person initially that would be infected. They would spread it to other people, maybe these other 4 people, but the time at which we started keeping track, there were 5 people that initially had the disease, okay? So P of 0 is 5 people, essentially. All right, so that's A. B, it says, how fast is the disease spreading after 3 months? How fast is the disease spreading after 5 months? Well, if you break down the sentence there, it says, how fast? Well, fast, thinking of the units on this, if I were to create a units for how fast the disease is spreading, if P represents people and T represents months, then the rate, how fast it's spreading would be people per month. And so that tells you what you need to do. If this unit of measure is in people, then if I want to get to people per month, I have to take the derivative. The derivative is the rate at which something changes. So we're going to go ahead and take the derivative of this. Now, there's a couple ways to take this derivative. I'm going to just go for it straight out of what I see here. I see a quotient rule, I see an exponential, and I also see a chain because the exponential has a function inside of that. So we'll use the quotient rules as the general framework. The derivative of the top is 0 times the bottom, 1 plus e to the 3 minus t, minus the derivative of the bottom. Well, the derivative of 1 is 0. What's the derivative of e to the 3 minus t? Well, that would be e to the 3 minus t, and then times, what's the derivative of the exponent? Well, times negative 1. So that's the derivative of the bottom, and then times the top, all over the bottom squared, so it's 1 plus e to the 3 minus t, and then all of that is squared. I'm going to simplify this a little bit, just a little bit, because 0 cancels all of that out. I've got a negative times a negative 1 and the 100 there, so we can say 100 times e to the 3 minus t. I guess I didn't need those parentheses there, right? All over 1 plus e to the 3 minus t squared. Okay? And so I'm looking for how fast the disease is spreading after 3 months. Well, that would imply that I want to find p prime of 3. So that'd be 100 e to the 3 minus, oh, look at that, 3, over 1 plus e to the 3 minus 3, and then squared. Well, that simplifies pretty nicely. 3 minus 3 is 0, e to the 0 is 1, so the top is just 100, and the bottom is going to be 1 plus, well, 3 minus 3 is 0, e to the 0 is 1, and then we have to square that. And so that's going to simplify to 100 over 1 plus 1 is 2, squared is 4, so that reduces to 25. So we can say that the rate at which people are being infected with this disease 3 months into time, basically, or after 3 months of its initial spread, is 25 people per month. Okay? So that gives us an idea, if we can model these kinds of infectious diseases, if we can create a model and they generally follow something that's similar to this, right? We can figure out pretty quickly when we're going to get a peak in terms of the rate, when we're going to start maximizing and all of that. And at the beginning of the coronavirus, we had a lot of mathematicians and scientists predicting when it was going to go away. And it very well could have gone away, but there's so many different variables that could go into play that it can knock our model out of whack. But again, if we can go back in time and look back, we can create a more accurate model. So with that said, that is part B here. And let me just make sure I am right. And so in fact, I am 25 people per month. All right, let's go ahead and take a look at the proof of this, okay? So the question is, all right, I told you that the derivative of e to the x is e to the x. And there's a couple different proofs for this, but I'm going to go about it in a simple way. We know that the derivative of e to the x is e to the x. Well, why do we know that? Because the teacher told me. Well, I want to prove it to you, at least in a basic way. I want you to remember, first of all, that the derivative of, the derivative of natural log of x is equal to 1 over x. Haven't gotten to the proof of that yet either, but we'll get there, okay? If I can somehow take this and rewrite this, I might be able to figure this out, okay? So let's do this. Let's say y equals e to the x. And the question is, or the thing we're trying to prove that y prime equals e to the x, okay? Y prime equals e to the x. So we would say, all right, well, I want to take the derivative of both sides because I want to get y prime. But then I'd be getting the derivative of e to the x, which in theory I don't know yet because I'm trying to prove this. So how could I rewrite this in a way that would help me see it? Well, I could rewrite this as a logarithm, and because the base is e, I can use natural log. So if you're just thinking algebraically, if you were to take the natural log of both sides, okay, you end up with the natural log of y equals the natural log of e to the x. Now you have to remember your rules of exponents. The rules of logarithms. Remember, when we're taking the log of something raised to a power, that power can go to the front. And so we're left with natural log of y equals x times natural log of e, right? Now, I can simplify this pretty easily because natural log of e, what does that mean? It means e raised to what power gives you e. Just like if I were to say log base 10 of 10, well, that means 10 raised to what power is 10? Well, that's 1, right? So e raised to what power is e, right? Natural log has a base of e. That's going to be 1 here. So we're left with x times 1. So now we have natural log of y equals x. Now, I could convert it back to exponential, but that's not going to be useful. I know how to take the derivative of natural log right here. The derivative in respect to x of natural log of x is 1 over x. So I'll take the derivative of this, but I got to think implicitly because y is the function now. So the derivative of natural log of y is 1 over y times y prime, because y is a function, right, in respect to x, and I have to apply the chain rule there. So the derivative of the outside thing is 1 over y, and then times the derivative of the inside, which is y prime. The derivative of x is just 1. And then we can isolate y prime by multiplying both sides by y. So we end up with y prime equals y. Okay, well, there it is. Y prime equals y. Well, what was y? Y, back here in the prompt, it said y equals e to the x. Therefore, y prime equals replacing the y value with e to the x. And therefore, we have just proven that the derivative of e to the x is e to the x. That's pretty cool stuff, right? Now, I'm going to go back to the definition of derivative and actually prove it a different way in just a second, probably the more traditional way in just a second. So just going through the motions here, making sure that everything looks good. And we end up with y prime equals 1 over x. Oh, interesting. Interesting. Okay. So there I proved why the derivative of e to the x is e to the x by using natural log of x. In this case, actually, what I have on the slide is going backwards. And so what I'm trying to do there is I'm trying to prove that the derivative of the natural log of x is 1 over x. Okay? And so remember, in the past I told you I was going to prove this for you, and here is the proof. Now we're going to have a little bit of a problem here logically, and we'll talk about this in a second. But here I'm going to say let y equal natural log of x, and we're trying to prove that the derivative of this is 1 over x. So we'll rewrite this in exponential form. Since that's a base e, we'll do the heart method, if you would, if you had a teacher that explained it that way. But this is a base of e, natural log. So we'd say e to the y equals x. And then from there, the derivative of e to the y, exponential, but it's also chain rule, implicit differentiation. It would be e to the y times y prime, right, because the derivative of y is y prime, equals the derivative of x is 1. So y prime equals 1 over e to the y. Well, what was e to the y? E to the y was x according to this, so we can say that y prime is equal to 1 over x. And there you go. Now, some real deep thinkers here are going to be saying, wait a minute. Logically, you're going in circles, and I am. It's called circular reasoning. I used the derivative of natural log to come up with the derivative of e to the x. Then I used the derivative of e to the x to come up with the derivative of natural log. So that's a constant circle, and so logically it's flawed, right? So that means we have to prove one of these outside of using the other, if you would, okay? Now, I'll go ahead and prove the derivative of e to the x using the traditional form. There's just one problem with it. There's one problem with it because we have a limit here that we may not know. It's something that we need to develop later on, okay? So I'm trying to find the derivative. So remember, the derivative is equal to the limit as h approaches 0 of f of x plus h. In this case, it would be e to the x plus h minus f of x, which is e to the x, all over h. And so from here, I've got to figure out a way to calculate this out. Well, what do I see? I see that I have an exponent here, e to the x plus h. Remember when you're adding exponents, what does that mean? Let me go back to a basic example. If I said 3 to the 5th times 3 to the 2nd, well, what is that? That's 3 to the 7th. Why? Because we add the exponents. That's way back in middle school, I believe. We add the exponents. Well, here we see a sum in the exponents. So I could actually rewrite this like this with two different bases. So I could say e to the x times e to the h. I'm rewriting that. And then minus e to the x all over h. Now on the top, I have a common factor of e to the x. So that's going to say limit as h approaches 0 of e to the x times e to the h minus 1, and then all over h. All right, so once I have this, I can actually break this apart. So I can say limit as h approaches 0 of e to the x times e to the h minus 1 over h. Mathematically, that makes sense. When I'm multiplying fractions, I would put that over 1. So I get e to the x times this over 1 times h, same thing. Then I'm going to break this apart and say, well, that's the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Well, because this first limit doesn't have any h's in it, we can just say, let me write this up here, we can just say y prime for this first part is e to the x, right? The limit as h approaches 0 of e to the x is e to the x. And then the limit as h approaches 0 of e to the h minus 1 over h, this is something that needs to be proven at a later time, or at a different time, I should say. But the limit as h approaches 0 of this guy is just 1. Kind of like the limit as x approaches 0 of sine of x over x is also 1. But it's kind of the same idea. So we can see that y prime equals e to the x. And so here we have a different way of proving the derivative of e to the x is e to the x outside of using the idea of natural log, so that we're not constantly using circular reasoning. And again, now this proof depends on this statement right here, if this is truly 1 or not. And I'm not going to spend the time in this video proving why that's 1. You can research that on your own. It's pretty much out there everywhere. All right, so that's that. And so now we want to keep in mind those two things that we now know. We know that the derivative of e to the x is e to the x, and we also know that the derivative of natural log of x is 1 over x. Those are the two things we know. With that said, we can now pretty much determine any derivative we want if we can rewrite any logarithm or any exponential function in these forms. We'll do more of that on another lesson. So for now, let's go ahead and do some practice with these specific functions and finding their derivatives. Okay, so the first one here, we have the derivative of natural log of 4x, I'm going to put parentheses around that, times e to the 4x. We're trying to figure that out. Well, what do we see? We see that we have a product here. We have a natural log function that's a composition, and we have an exponential function that's a composition. So taking the derivative of this, we're going to use the product rule. So what's the derivative of the first thing? Well, the derivative of natural log of something is 1 over that something, so 1 over 4x, and then times the derivative of that something, so times 4. That's the derivative of the first piece. Then times the second piece, plus the derivative of the second piece. So the derivative of e to the anything is e to the anything times the derivative of the anything. So we're using the chain rule again. And then times the first piece. So times natural log of 4x. We can maybe simplify this a little bit because the 1 over 4 times 4 reduce. So we're left with e to the 4x over x. And then plus over here, we would end up with 4e to the 4x times natural log of 4x. So that is our first example, dealing with exponentials and logarithms together. All right, let's make sure that is correct. And it is. Okay. For number 2, let's go ahead and, interesting. Let's go ahead and do number 2 over here. Number 2 says y equals the natural log of x. All right, well, we have a chain rule. We have a function inside of another function. So what is the derivative of the outer thing? Well, the derivative of the outer thing is 1 over the inside, so 1 over natural log of x, times the derivative of the inside thing, which is 1 over x. And then you can simplify that a little bit to say 1 over x times natural log of x. All right, that's number 2 there. And number 3. Number 3 is going to get some students. It happens every year because they're not thinking about what a constant is, what a variable is, and what a function is. Okay? So for number 3, it says that f of x is equal to the natural log of 5 times the natural log of 5x. What is f prime of x? Well, some students might say right away, I'm going to use the product rule. And there's nothing wrong with using the product rule. In fact, I'll go ahead and do it here so you can see it. So we can see for some of us that the natural log of 5 is the first function, and the natural log of 5x is the second function. The problem that we have is when we use the product rule, we're trying to find the derivative of natural log of 5. I see a lot of students say, well, the derivative of natural log is 1 over the thing, so it's 1 over 5. No, it's not. No, it's not. The derivative of natural log of x is 1 over x. But natural log of 5, that's not a variable. That's not a function. That is a constant value. If you were to type natural log of 5 into your calculator, you would get a number out. So this is equivalent to, it's akin to saying, what if y equals 7 times natural log of 5x? What's the derivative of this? Well, again, you could use the product rule. You would say y prime equals, what's the derivative of 7? It's 0. And then times natural log of 5x plus blah, 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 blah. This is the same type of thing. This is a constant. Just like the sine of pi is a constant. It's not a function or a variable function, if you would, or it is a constant function. But the bottom line is the derivative of natural log of 5 is 0. And then times the second thing, so times natural log of 5x, plus the derivative of the second thing. Well, the derivative of natural log of something is 1 over that something times the derivative of the inside, which would be times 5. And then we would take that and multiply it by natural log of 5 over there and get our answer. So this simplifies to f prime of x equals the 5 over 5 reduce, and so you're left with natural log of 5 over x as an answer there. Okay. Now I will go back and talk about that briefly just so we can make sure that we're good with that. Looking at the natural log of 5, if I were to just say y equals the natural log of 5 and want the derivative, Well, we already know that it's 0 because of what I explained. But if you were to treat it as a function, if you were to treat it as a composition of functions where 5 is the inside, you can do that. But you got to make sure you apply the chain rule properly. What's the derivative of natural log of anything? Well, it's 1 over that anything. But then we have to apply the chain rule. So we'd have to multiply it by the derivative of that something. Well, what's the derivative of 5? It's 0. So y prime equals 0 ultimately. Okay? So the derivative of natural log of 5 is 0. It's a constant value, so the derivative is 0. Whereas over here, the derivative of natural log of x is 1 over x. And if you wanted to use the chain rule, you could. The inside of x, or sorry, the inside of natural log is x. So what's the derivative of x? We would say times the derivative of x is 1. Well, that doesn't change anything. So that's just some interesting things, some important things that you're going to want to consider as you take your derivatives. All right, and the last problem for today, number 4, we have the derivative in respect to x of e to the 2 over x. And we want to take this derivative. Okay, well, I recognize right away that I have e to the something. So I know that the derivative is going to be e to the 2 over x, right? But then I have to take the derivative of that 2 over x. And now I could use the quotient rule if I want, but I don't want to. I want to simplify this so that I can easily take the derivative. So I'm going to rewrite this as e to the, what's 2 over x? We could rewrite that as 2 times x to the negative first power. Right? 2 over x is 2 times x to the negative first power. That just helps me take the derivative of that exponent up there. So the derivative of this whole thing, recognizing that the exponent is an inside function, this is a composition, would be e to the 2x to the negative 1 times, what's the derivative of that? That's just power rule, times negative 2x to the negative 2. And then we could simplify it. We could write it so there's no negative exponents if we wanted to. We could then write this as e to the 2 over x again. And then times, this would be negative 2 over x squared. And then we could even simplify that further by saying negative 2 e to the 2 over x all over x squared as a final answer for that derivative. Okay? All right, let's make sure I am correct there. And I am. All right, so we actually covered something very, very important today. The derivative of e to the x is itself is e to the x. And then, of course, based on that, the derivative of natural log of x is 1 over x. And then we applied that using the chain rule, product rule, and all different kinds of rules. Hopefully you have a good understanding of that, and hopefully I made your brains think a little bit when we're talking about infectious disease and how calculus relates to that kind of stuff and understanding growth rate and things like that. So if you have any questions, please comment below. Don't forget to like and subscribe, and I will talk to you later.